everyone, I'm Chen. Today I'm going to present our recent work, ThunderGP HLS-based graph processing framework on FPGAs. Nowadays, graph processing has been a very important application in data centers because, as you know, the graph data structure can represent the data set from many application domains. For example, social networks, cybersecurity, and machine learning. At the same time, FPGAs are attractive for application acceleration in data centers. For example, Amazon just deployed the FPGA in their cloud and some hardware service. This benefit from fine-grained parallelism, low power consumption, and especially extreme configurability. So under such case, graph processing on FPGAs has been extensively studied. In this page, we survey the existing FPGA accelerated graph processing frameworks. We basically survey the framework and the library and also the dedicated accelerator architecture. From this survey, we have the following observations. Firstly, most of the work do not have explicit APIs, and also most of them are programming with hardware description language, for example, Verilog or with HDL. In terms of automation, most of them don't have. That means that developers need to conduct the manual performance tuning. In terms of usability, as we can see, most of them are based on the simulation. I believe there is a gap from the simulation to real hardware implementation. And also, most of them are conducted on a few applications and also are not publicly available. So, in summary, existing works have poor programmability and also they require manual performance tuning. For example, pipeline composing and design space exploration, and the usability is not that good because they are not open source and there is no ready-to-run systems. So we think there is no gap between high-level graph processing applications and the underlying FPGA platform. So we conclude there is a need of easy-to-use and high-performance system for supporting graph processing on FPGAs. Of course, there are a set of challenges to achieve high throughput and easy to use. Here, I will talk about our solutions for these challenges. So the first challenge is that we need to support different graph processing algorithms because, as we all know, there are too many graph processing algorithms such as BFS, SSP, PageRank, CC, WC. So to address this challenge, we actually design an efficient architectural template with the adoption of the guest model as the abstraction of different algorithms. Secondly, it's very important that we can enable programming without hardware expertise, because as we all know, the graph application developers are mainly from data science domain, so they are not familiar with hardware description programming. They should be familiar with C or even Python. So in order to address this challenge, we only expose the high-level APIs to developers. And we take the rest to generate the hardware accelerator and also the bit stream. So thirdly, it's very important. The state-of-the-art FPGAs usually have multiple SLRs that provides massive resources and memory bandwidth. So it's very important we can analyze all the potentials of these platforms to achieve a high performance. So to address this, we explore some heuristics to scale our architectural template to multiple SLRs, and also we schedule the graph data correspondingly to keep the computer busy. So all these solutions are integrated in our work, ThunderGP, which is an HLS-based graph processing framework on FPGAs. So in the next, I will introduce ThunderGP from the following aspects. Firstly, I will show the overview, and then the architectural template, and also our automated design space exploration for multiple SLR FPGAs. Then I will introduce the graph partitioning and scheduling. Finally, I will be the evaluation and conclusions. So let's start with the overview. Okay, this figure shows the overview of ThunderGP. As you can see, in the second row, these are main intrinsics of ThunderGP. The first component is accelerator template, which provides a general and efficient architecture for different graph processing algorithms. It adopts the guest model, which I will introduce later. And also the accelerator generation, which takes the input from developers and also as well as the accelerator template to generate a sensitizable accelerator for the FPGA platform. The graph partitioning and scheduling manage the graph data to coordinate with the accelerator the system generated. So in terms of workflow, the developers just need to assign the functions or scatter, gather, and apply to the system. And the developers also need to assign the underlying hardware platform because the system requires some specs of the FPGA platform, such as a number of SLRs and memory minimize, this kind of stuff. In the next, the system will automatically generate the accelerator. And after the accelerator is generated, the developer just need to assign the graph data to the APIs for graph partitioning and scheduling. So finally, the application is running on the underlying platform. Currently, ThunderGP relies on the Xinyu development environment. So in the next, I will introduce the architectural template. So as I mentioned before, our architectural template adopts the guest model for graph processing. It contains 3 stages: gather, scatter, and apply. So for the scatter stage, basically for our edge, an update tuple is generated with format of destination and a value. So let's take this example graph as the example. For example, the vertex 1, it has vertex 7 and 2 as its neighbor. So in this case, 2 update tuples will be generated with destination of 2 and 7 respectively. And also the x, y are calculated by the vertex 1's property and also the edge properties. So for the gather stage, basically it accumulates values to destination vertices. So in this case, the x and y will be accumulated to the property of vertex 2 and vertex 7 respectively. So we firstly need to read their property and accumulate with the value and then write back. So after all the edges finish the scatter and gather stages, an apply function is applied on all the vertices for the next iteration. As you can see, the guest model has 3 function stages. So correspondingly, we expose 3 functional APIs to developers, so the developers can, modify these 3 APIs to achieve different hardware accelerators. This guest model is highly optimized in our architectural template to provide a good performance for different graph processing algorithms. Firstly, ThunderGP adopts the vertex buffering with RAMs because, as you can see, the neighbors of one source vertexes may be very far away from each other. So it will introduce a lot of random memory accesses. So if we buffer the vertexes into the RAMs, then we can avoid random memory access. Secondly, ThunderGP adopts multiple PEs. As you can see, we have multiple scatter PEs and gather PEs. This is a common way to improve the throughput, to improve the number of edges processed per cycle. Especially ThunderGP adopts a shuffle logic. So the basic idea is this. Let's say these 2 tuples are generated from the scatter stage in one cycle because we have multiple PEs. And also we have multiple scatter PEs that consume the tuples from the scatter stage. So in this case, the P0 processes the vertex 0 to 3, and P1 processes the vertex from 4 to 7. So this shuffle logic will dispatch these 2 tuples to corresponding PEs in parallel and on the fly. So the first tuple will go to the P0, and second will go to the P1. So by this shuffling, we can avoid data reordering because, as you can see, that this shuffling resolves the data dependency at runtime. And also, we can enlarge the graph size processed on chip because different PEs can process different vertices. So in this way, we don't need to replicate the vertices for different PEs. So we can have a larger partition size, and then we can reduce the replication factor of the graph processing, hence a better performance. Finally, we pipeline the scatter and gather inside FPGA. As you can see, the scatter PEs and gather PEs are connected by scaffolds inside FPGA. So it's different from the BSP execution model from existing work, where the execute the scatter for all the partitions and then write back to the global memory and then execute the gather stage. So in this way, we can reduce the memory accesses to the global memory. And also we have a longer pipeline, so we can exploit the pipeline parallelism better. However, one side effect is that we need to access the source vertices from the global memory directly. As you can see in this figure, the first row is the source vertex properties in the global memory, and the second row is the request from the scatter stage. As you can see, the access is not sequential anymore because for some vertices you don't need to access it, and also for some vertices you need to access it for multiple times. But unfortunately, with HLS, without any optimizations, each access will issue one request to the global memory that will heavily store the pipeline, resulting in a very bad performance here. So by analyzing the memory access pattern, we hence deploy 4 memory optimizations. The first one is caching, because as you can see, different data blocks build very good data locality. It will be accessed for multiple times. The second one is coalescing, because the memory requests from scattered PEs are not too far away from each other. So we can coalesce them into the less number of memory requests to improve the memory efficiency. The third one is prefetching, because the source vertices are already in the ascending order for the standard CSR or COO graph format. So we can prefetch the data for future use. The last one is execute access decoupling. So this plan is not replicated in this figure, but the basic idea is that graph processing, the throughput is fluctuating. So if we can decouple the access and the execute, then sometimes the access can be ahead of execution. Then we can further reduce the possibility of pipeline stall. So these are all about the optimizations of the architectural template. So in the next, I'm going to show you how we utilize this template to fully utilize the resources and memory bandwidth of multiple SLR FPGAs. Basically, we have 2 principles. Firstly, we never let kernels cross SLRs because, as we all know, that will lead to bad timing and a lower frequency. Secondly, we fully utilize the memory bandwidth of the platform because essentially graph processing is memory bounded. So if you want to achieve a very good performance, then we must fully utilize the memory bandwidth. So guided by 2 principles, we have 2 automatic steps in ThunderGP. Firstly, we calculate the required number of kernels for the platform, and then we try to fit the kernels into multiple SLRs. So let's look at the first step, calculate the number of kernels. We firstly calculate the kernels for one memory channel, find the equation 1 and 2. So the basic idea is this: given the input from users, then we know the RI of each PE, and then we also know for each iteration how much data we need to read from the global memory, and also we know the data wise of the memory channel. Then we can calculate how many PEs we need to meet the bandwidth of one memory channel. So in the next step, we just scale the number of kernels to the number of memory channels. Let's say this example. For one memory channel, we just need 16 gather PEs. Let's assume that. And let's say we have 4 memory channels, and we just duplicate the number of kernels to 4 times. So then we try to fit these kernels into multiple SLRs. Basically, we model it as a multiple next-stack problem, because for different SLRs, they have different capacities, because there are some static region occupies a lot of resources here. And also for different kernels, they have different fits. So we model as a multiple next-stack problem. Then we try to fit them into the multiple SLRs by tuning the parameters of the scatter of all the kinds of PEs. So yeah, we fit them into SLRs, and finally we interface kernels with the memory channels to produce the synthesizable code for the development environment. So far we have the accelerator architecture for the FPGA side. In next, we need to manage the graph data to coordinate with the accelerator to fully utilize the compute. So the first one is graph partitioning. Because we adopt vertex buffering, however, the VRAM or URAM size on FPGA is pretty limited. So we first need to partition a large graph into smaller chunks to let them fit into the FPGA. So ThunderGP actually adopts a very low overhead graph partition method. Basically, it's a destination vertex count. Let's say this example graph. This is the original format with the CO format, and we have edge list and vertex set. Let's say the FPGA can buffer 3 vertices. Then we just simply divide it into 2 partitions. The partition 1 with the vertex from 0 to 2, and the partition 2 with vertex from 3 to 5. And also for each partition, it contains the edges whose destination vertex is in current vertex set. So as you can see, for this partition method, there is no edge reordering or sorting operations. And also the complexity is just OE. So it's a very low processing overhead. So in next, we need to schedule these partitions to the accelerator, because we have multiple SLRs and we have multiple kernels and multiple memory channels. So the first step we do is divide a partition into multiple chunks with edges equally partitioned. The benefit is that for some small graphs that only has 1 partition, we can still fully utilize the number of compute units here. So in next, we actually proposed a regression model to estimate the execution time of each chunk. Then with this execution time, then we can use a gradient solution to find the optimal scheduling plan. So finally, we can schedule the chunks into the hardware units. Yeah, that's all about the graph data management. In the next, I will show you the evaluation. So we conduct the experiments on 2 hardware platforms and 7 applications, as well as 14 datasets, publicly available datasets. Firstly, we evaluate the memory optimizations of the accelerator template. As you can see from this figure, 4 methods cumulatively contribute to the performance, and the final speed up can be up to 32 times here. Then we evaluate the scalability by varying the number of SLRs and number of memory channels. As you can see from this figure, our scalability is very close to the maximum theoretical speed up, which is 4 here, because we have a total of 4 memory channels for different platforms here. Lastly, we compare ThunderGP with the state-of-the-art implementations. Firstly, we compare with RTL-based solutions, where we deliver up to 2.9 absolute speed up and 5 times bandwidth efficiency speed up. We then compare with the HLS-based work, where we deliver up to 30 times absolute speed up. We also compare with our previous work, where we deliver 5.2 absolute speed up. Finally, ThunderGP is publicly available. You can find it on GitHub, and also it's featured at Linux apps and libraries. So for conclusions, basically in this work, we identified the gap between high-level graph applications and underlying CPU FPGA platforms. We then proposed a framework called ThunderGP to mitigate this gap. So ThunderGP finally delivers 2.9 times speed up over the state-of-the-art even RTL-based work. And more especially, ThunderGP is based on the real hardware implementation, while this state-of-the-art work is based on simulation. More importantly, with ThunderGP, the developers only need to write a few high-level functions without any hardware expertise. Finally, is the acknowledgement. So that's all about my presentation. Thanks for listening.